And the way we define this is we take a loop gamma in the fundamental group, and this maps to +1 if gamma lifts to a loop in the orientation double cover. So if you had a little loop here and that lifted to a loop here, that would get +1, and it maps to -1 if gamma lifts to a path, so not a closed loop in the double cover. So in this example, a loop going round the Mobius band once would lift to start here, go around, and then it would have gone to the other sheet of the cover. And this lifts to a path and not a loop. So this would get a value -1 under the orientation character. So looking at this, it immediately follows that the first Stiefel-Whitney class is the obstruction to being able to orient M. As soon as you have a loop in M that maps to -1, or a loop in M that lifts to a path in the double cover, you know that you can't get a consistent choice of generators, because if you go around that loop, you switch generator when you get back to here. And so this isn't a globally consistent choice, because you have this jump as soon as you go around a loop. So that means you can't orient M. Now this orientation double cover isn't going to be the only covering space of interest to us in this lecture. If we take this double cover, we can embed this, can be embedded into a larger covering space. Again, I'm going to use suggestive notation, M sub Z. Before, over each point we had a copy of Z mod 2. Now over each point we're going to have a copy of the integers. And this is sometimes called the orientation sheaf of M. Now this is defined in an analogous way. So before we were just taking the generators of all our local homology groups. Now we just take any class. So this is all the homology classes alpha of x for points in M where alpha of x is anything in HM of M rel, everything except the point. So now, as I said, you should see that, well, there's a copy of the integers over each point now. It's not a two-sheeted cover anymore. It's got, well, Z sheets. And we can topologize this again in exactly the same way. Now, let's observe how this covering space looks. every local homology group has a 0, we have a sheet of mz which is just 0 at every point, and this gives us a copy of m in the cover. So at alpha of x identically 0, we get a copy of m. And then I claim that for each positive integer we get a copy of the double cover. And this is given by plus or minus n times mu x for mu x a generator. So let's just do a quick example of how this looks. So first of all, an easy example. If we just take a copy of the circle S1, so there it is. The orientation double cover is just the product of S1 with Z mod 2. It's orientable, so we just get this 2-sheet cover. And then again, this cover with fibre Z is just going to be S1 cross Z. It's just a product. So we get one copy of S1 for each integer. This is all because M is orientable. How about the Möbius band? Well, we already saw what the orientation double cover looks like. So, well, here's M, which I've tried to draw sort of flat. The double cover, as before, we had something that looks a bit like this. So 2 sheets and orientable. And then this M sub Z is going to be a single copy of the Möbius band in the middle. So this is at the height 0. Then we get all of these, the height 1 and height minus 1 crossing over, something like that. And then 2 crossing over with minus 2, and so on and so forth. Possibly drawn like this at each height. So now, with this picture in mind, we'll explain what it means to choose an orientation in terms of, well, these kind of covering spaces. So if we have a continuous map from M to this M sub z such that x maps to alpha x in this local homology group, then this is called a section of the covering space. So we've got some continuous map from the base space up to the covering space, which it then projects back down to give the identity. This is a section, and then we note that an orientation of M is the same thing as a section where we map to a generator over each point. Not just any old class, it has to be a generator. So in particular, I mean, we do have sections do exist in this non-orientable case. You can take the zero section. This doesn't give us an orientation though, because 0 is not a generator. A generator would have to map to the double cover at height 1 and minus 1. In the case for z coefficients, this is. In a moment we'll generalize to coefficients in a ring, where this more general treatment will be useful. So now let's replace the integers with any commutative ring. R. And importantly, whenever I refer to a ring, my ring will have an identity. And we can generalize the notion of an orientation to an R orientation analogously. So we say that an R orientation is a section from M to M sub R. Now this should be clear what I mean by M sub R. Over each point we have this local homology group with coefficients in R. So over each point we get a copy of R. I mean, we replace Z with Z tensor R, which is just R. So this is a section, again, such that x maps to mu x, a generator. Well, now we should consider what it means to be a generator in a ring. Well, any invertible, any unit, rather, in the ring is a generator. So, i.e., mu x is a unit in R. And again, we have local consistency